So if you remember, yesterday we talked about the topological conjugacy of interval diffeomorphisms with two fixed points. And now we will try to generalize and look at interval diffeomorphisms with several fixed points. So first of all, let's see what a fixed point can look like. Like, there are many different kinds of fixed points. So this is the interval 0, 1, right? So we draw the graph F. So as we said, orientation-preserving interval diffeomorphism must have 0 and 1 as a fixed point. Okay, it can have other fixed points. So there's several ways in which, so every point at which the graph intersects the diagonal is a fixed point. Right? What is the maximum number of fixed points we can have? For orientation preserving. How many infinitely? Countably? Can we have uncountable?
Yes, of course, the diagonal itself.
Yeah.
Yes, y equals x.
The identity map.
Yeah.
Every point is a fixed point. Right? We can also have something in between, so we could have something that looks like this, and then we could intersect the diagonal for some interval, and then it can go like this, right? So here we can have an interval of fixed points, right? Then we can also have, so we can have something like this. We can also have a fixed point that is tangent to the diagonal. Like this, that is a fixed point. The graph can be tangent to the diagonal. And then we can have fixed points where this is kind of transversal to the diagonal, like this. Right? So there are various possibilities. In particular, what is the derivative at this point here, at these fixed points here, the derivative of the graph?
1.
Is 1. What about at this point where it's tangent? 1, right? So if the derivative is different from 1, then it cannot be tangent. Right here, the derivative will be different from 1. Also, here we might have, we could do like this. Wait, that's not a diffeomorphism, but we could have this. So here the derivative has to be different from 1. Obviously, since the diagonal has slope 1, if the graph kind of crosses the diagonal, then the derivative will be different from 1. Right? Whereas if it's tangent here or here, then the derivative will be equal to 1. So it turns out that we want to distinguish these two cases for several reasons. So we will say that definition. So this is always in the context of interval diffeomorphism, right? So for the moment, everything, because we will have similar definitions in other settings, but definition. P, so if f of p equals p fixed point is hyperbolic if the derivative is different from 1. If the I will put, well, let me put an absolute value here, because if it's, so it applies to the orientation reversing case as well, right? So although in the orientation preserving case it cannot be equal to -1 because it has to be monotone. But in this definition will apply also in the orientation reversing case. So what can happen? So lemma, suppose Fp equals P and F prime of P is between 0 and 1. Okay, so now we're going to do a little local analysis of this. So suppose that we have here a fixed point where the derivative is less than 1. So let me zoom in to this situation. We have here the diagonal, and we have here the graph. This is the point P. Okay, and we have the graph is doing something like this. So f prime of P is less than 1, right? Because it's like this. So what can you say about this fixed point? What's going to happen to the points? So here we have, in some sense, the graph, right? I'm zooming in and I'm thinking of the graphs here. So if we take a point X here, what is it going to do?
Cross the diagonal.
Sorry?
Cross the diagonal from one side to other side.
How does it cross the diagonal?
I mean, the points before the P point, the curve cross the diagonal.
The curve crosses the diagonal. What about the dynamics of the point? Okay, then what can you say about Fn of x?
Attracting,
And
before
gross.
that point is attracting maybe.
Its growth is less than the growth of the diagonal.
Excuse me? Yes, this is less than the growth of the diagonal. So what does this imply?
So after P is repels dynamic.
What?
It
Say
also-
it repels dynamic.
It repels?
Yes, like it,
Why does it repel?
the dynamics of it.
So let's try to do a graphical analysis of this, right? So f of x is here. Okay, remember, I'm going to do kind of locally what I did here. So you take a point here, x, right? You look at f of x, which is here, and then remember we went across to the diagonal. So you take x, you go across to the diagonal, and then you come to this point here. So f of x is here. You agree with that? Yes? And where's the next image? The next image would be there, there. It's converging to P. Why did you think it was repelling?
Because I mean, the image f of x for me was on the other side. So I thought it evolved to the right side.
Right. But you can see now that it's converging towards P. Yes? So another way to look at it is the following. So suppose, well, we have not proved anything yet, right? This is just a sketch. Now we would like to prove, so the lemma would say, suppose f, so let's suppose f is a C1 diffel, okay? And suppose we have a fixed point with f prime, then Fn, then there exists a neighborhood. Or let's just, then a P is an attracting fixed point. Remember the definition of an attracting fixed point? There's a neighborhood of points that converge to P. So we need to prove that this picture is correct. So this picture suggests that if you take a point and you map it here, then it will be converging to P. If you take a point here and you map it here, it will be converging to P. So there's two ways, at least two ways to see this, which are quite elementary. One is just the same argument we used the other time. Now, these are monotone maps. So we need, okay. Let me say, I'm going to leave the proof as an exercise, but we're going to sketch it a little bit here. Okay, so let me say one approach to this is that if the derivative here is less than 1, okay, let me give the proof. Okay, let me give one proof. So, since f is C1, what does it mean that f is C1?
The derivative is continuous.
The derivative is continuous, okay? And the derivative at the point P is strictly between 0 and 1, okay? So that means that there exists a neighborhood where this continues to hold, okay? F is C1, there exists a neighborhood N of P P such that f prime of x is in 0, 1 for all x in this neighborhood. Very good? Yes? So what does that mean? Moreover, and f of NP is mapped strictly into NP, right? Because this follows simply from the fact that the graph, you just take 2 points, of this neighborhood, and you can see because the derivative here is between 0 and 1, then it means that the graph crosses the diagonal, which means that on one side of the diagonal it's above the diagonal, on the other side it's below the diagonal. So when it's above the diagonal and you take a point, then its image will be greater than x, and when it's below the diagonal, if you take a point, its image will be less than x. They're monotone in opposite direction, right? And since, okay, that's the explanation. I think I don't need to write it. It's pretty clear. There's a neighborhood here. This is the neighborhood N P, which is mapped inside itself because of this property that on one side the graph is above the diagonal, on one side is below. If it's above the diagonal, the property of a graph being above the diagonal means that f of x is greater than x, right? Because if you take x here, then the corresponding point x is on the diagonal. The point f of x is above the diagonal, so it's greater than x. Whereas if it's below the diagonal, it's less than x. So this one moves to the right, and this one moves to the left. So the neighborhood is mapped inside.
But if we take a point before P, and okay, it could be that the point, the f of P flips to the other side, right?
Not if it's a diffeomorphism, because otherwise you would have, you cannot have the derivative, you cannot have negative derivative here, right? So you're thinking of this picture, you're thinking of a picture where it is like this.
Yes.
Yes, that can happen in the orientation reversing case. Yes, that can happen. And then you may have an attracting fixed point where it's still attracting, but things flip around. Okay, it's a slightly different geometry. We can look at that later. But as we said, we're going to focus on the orientation preserving case for the moment. Okay, so we have these two properties, 1 and 2. Okay, so now that means that if we take 2 points, so let xy be in this neighborhood and P, okay, then what can we say about the distance between f of x and f of y?
Smaller than the distance between x and y.
Why?
Because it is approaching P.
Well, approaching, yes. So so the fact that the derivative is strictly less than 0, 1, so maybe I could say, in particular, there exists lambda, okay, such that the derivative f prime of p is in 0 lambda. There exists lambda less than 1, such that f prime of p is in 0 lambda. You agree with that? Yeah? So it's not just between 0 and 1, it cannot get arbitrarily close to 1, because if we take a sufficiently small neighborhood, then this is strictly between 0 and 1, so we can bound it away from 1. Okay? So now we can use the mean value theorem for this. What does the mean value theorem say about if you take 2 points, x and y, you take 2 points, x and y, and you look at the images?
That's equal. The difference between the images are equal to a constant, well, the derivative, some form.
Exactly, right? So, anyway, by the mean value theorem, there exists some z in the interval xy, okay, such that the distance between f of x and f of y is equal to the derivative, the absolute value of the derivative is z, times the distance between x and y. You agree this is the mean value theorem? Yes? So we take a point x, y, and there's some point z inside, such that the distance between the images is exactly equal to that. And what do we know? We know that this is less than or equal to lambda. That's why I wrote this, right? So this is less than or equal to lambda x minus y. And what does that mean? Is that so f is a contraction on this set NP, and by the contraction mapping theorem,
Conversion
there
has to
exists
be
a
one.
unique fixed point and every orbit converges to that fixed point. Okay? And therefore every orbit must converge to this big point. And so f and x converges to P for all x in NP. Okay, this is the this is really just the formalization of this picture, right? So you have locally, you have a unique fixed point. If map is C1, it uses the fact that map is C1 because the derivative changes continuously. So that means that you cannot have any other fixed point. This means that there exists some sufficiently small neighborhood where the derivative is very close to the derivative of P. If the derivative P is strictly between 0 and 1, then you can choose a neighborhood where the derivative is again strictly between 0 and 1, in particular less than some constant lambda less than 1, and therefore in this neighborhood it's a contraction. This neighborhood is mapped into itself, so everything must converge to P. We will all generalize this to higher dimensions also. This is a kind of very important theorem. It tells you that locally, it's just saying that locally, if the map is, it says something obvious, that if the map is in some sense a contraction at that point, because the derivative is less than 1, so the derivative is in some sense contracting, and then in a neighborhood it's also contracting. Okay. And of course we have an analogous statement if the derivative is less than is so lemma if f c1 f of p is equal to p and f prime of p is greater than 1, okay, then what happens? And this corresponds to this picture here. Here we have something that goes like this. Okay, the derivative is greater than 1, so that means the diagonal is crossing like this. Then what happens? Then if you take 2 points here, if you take a point x here, then here on this side it's above the diagonal, okay? So that means that its image is larger than what it is. So on the right hand side, on the interval you have kind of right and left, right? So on the right hand side it's bigger, so it moves away, right? So this is f of x, and then it moves away again, and then it moves away again, right? And the same thing on this side, it goes to here, it moves away, so it is moving away from here. But in backward time, this is a diffeomorphism, right? So it's invertible. So if you look at the pre-images of a point, then what happens? It goes in exactly the other direction, right? So if you look at the pre-image of the point, it's a little bit like looking at the map like this. This becomes an attracting fixed point for the inverse, okay? So remember what we call the analog of the omega limit point. P is an attracting fixed point, and here we say that P is a repelling fixed point. Remember, the repelling fixed point is a point such that there's a neighborhood where the alpha limit set of every point is that. So it's just a point where which is attracting for the inverse, if you will. Okay, so this is exactly the same proof. Yeah.
I have a question. Why we call this point with derivative less than 0, is it between 0 and 1 hyperbolic?
Yeah,
What's hyperbolic about that?
Yeah, it's really not a particularly good. It comes from a two-dimensional setting in which this analog has a kind of hyperbolic, has some hyperbolas. We will look later at some two-dimensional settings, and in that setting it makes more sense to think of certain conditions to be called hyperbolic. You will see, and so it's used in this setting. It does not really make sense, but it's just become a terminology that is used. Yeah. So what happens before we go on? So these hyperbolic fixed points play a very important role.
Sorry?
Yes.
Do you define hyperbolic to be not equal to 1 or between 0?
No, both of these are hyperbolic. Hyperbolic is just not equal to 1. Yes. Because 1 is a slightly degenerate case. So I just want to spend a few minutes thinking about what kind of behavior you can have. So can you have also attracting and repelling if the derivative is equal to 1? What can happen? Let's look at some cases here. So, for example, you could have derivative equal to 1 like this, just at this point. Let me draw it a little bit more. So suppose it's tangent here. Okay, I didn't draw it. It's difficult to draw, but suppose the derivative is equal to 1, so it's tangent there. So what is this point? Is this point attracting, repelling, neither?
It's attracting from one side and repelling from the other.
Well, in this case, it is attracting on this side and attracting on this side. The geometry is actually really the same as this one. Okay. What you may have, however, you may have it like this. And then indeed you have the situation where it is attracting on this side and repelling on this other side. Or like this, where it is now attracting on this side and repelling on this side. And then of course you have the analog of this corresponding to this. It can be tangent like this. So if the derivative is 1, the moral of the story is not so much that you cannot still have attracting or repelling, but that you cannot tell, right? Just by that information. So the remarkable thing about these two lemmas, which maybe are not so clear at the beginning, is that you're given information only about one point, and you are deducing information about the whole neighborhood of that point, right? So this is the remarkable thing. Of course, you're using the fact that the map is C1, but also in this other case, the map may be C1. And now if I tell you, okay, the derivative is equal to 1 at that fixed point, then it gives you no other information, then you do not know if you're in this case, in this case, in this case, or in the corresponding for this, which is the repelling case. You simply do not know. It's not so much a question, so this would be the case where you have like this. Right? In this case, you have repelling on both sides. You do not know. Okay? So you can have other information, so we can go a little bit finer in this analysis. For example, there is a difference in the second derivatives. Here. If you remember, the second derivatives is the behavior, is the rate of change of the first derivatives. So you can see here, if this derivative is 1, what is this derivative here? Is it bigger or less than 1? This is less than 1. Right? So this derivative is increasing towards 1. Okay? And here what is this? Also less than 1. Okay? So here this derivative is is increasing to 1, and then it's decreasing again. Okay? Whereas in this case, what is happening here? This derivative is less than 1, here it's 1, and here it's bigger than 1. Okay? So I don't want to go, because we could spend a lot of time on this, I don't want to go into the details of the analysis of all this. It's very interesting, but we can say, for example, if we know that the second derivative is non-zero, and if this, depending on whether the second derivative is positive or negative, for example here, in this case the second derivative will be, if the second derivative is positive, then we know that we are in this situation here, right? Because the second derivative is positive here, which means that the derivative is increasing at that point, so we have that kind of situation. So we can do some analysis, and we can, you know, in some cases we can put some, say if we know something about the second derivative, then we can distinguish between these different cases. Okay? Then of course there's also the case, the more degenerate case that we had before, in which you have a whole interval of fixed points, right? Which is an even more degenerate case. And of course in this case the points are neither attracting nor repelling, right? Because if you take a neighborhood of this fixed point, then the other points are all fixed, and so it's, yeah, they're not converging to this particular fixed point P, neither forward time nor backward time. Okay, so why are hyperbolic fixed points important? First of all, because just by looking at the point you can tell if they're attracting or repelling. And let's make a definition. Another definition over here. Definition. F is a C1 interval differential, is hyperbolic. If all its fixed points are hyperbolic. So now let's define the previous question that I asked, is how many hyperbolic fixed points? How many fixed points can a hyperbolic interval differential morphism have? Can it have countably many? So the exercise, this I will leave as an exercise. I think it's a very nice exercise. If F is a hyperbolic interval differential, then it has finitely many fixed points. Hyperbolic, of course, because by definition they're hyperbolic. Fixed points. So why can it not have countably many fixed points?
Because monotone function, if we take x minus fx is monotone function in this case, because if all derivative is continuous function, so all derivatives are smaller than 1, or this case. X minus fx is monotone function, or monotone increasing or monotone decreasing anyway, and so in this case we have
no, x minus fx is not monotonic decreasing, because you can have several fixed points. So the hint is that if you have a countable number, there must be an accumulation point.
Yes.
Right? So you just need to show two things. That this accumulation point must be fixed point, and then it's easy to see that this fixed point cannot be hyperbolic. Why is that? If it's an accumulation point of other fixed points. because of the study we just did, right? If you have a hyperbolic fixed point, it needs to have a neighborhood where it's attracting or repelling. It cannot be accumulated by other fixed points. Okay, so there's two steps. One is that hyperbolic fixed points are isolated. Isolated in the sense that they cannot be accumulated by other fixed points. Okay, this is, you kind of need to formalize this a little bit, but it's clear from the fact that we have it's a C1 map, hyperbolic fixed point. You can easily show that it cannot be accumulated by other fixed points. It follows by our lemmas, basically, right? And two is that by contradiction, if it had countably, so infinitely many fixed points, implies there exists some accumulation point, which must be fixed.
So, more or less, we can cover each one of these. Suppose that we have infinitely many, we can cover it with no, maybe no.
No, that doesn't give it enough, because you could still have countably many neighborhoods, disjoint neighborhoods. It's really, you need to use the fact that you must have an accumulation point. And then use the continuity of the derivative to show that this accumulation point, well, the continuity of the map, I think. Yes, the continuity of the map. If you have an accumulation point of fixed points, this accumulation point must be fixed. This is just the continuity of the map. And by contradiction, hyperbolic fixed points cannot be accumulated by other fixed points. Okay, this is an important exercise here to really get the feeling of this picture. Okay, so this is an important motivation for hyperbolic fixed points. Hyperbolic maps, hyperbolic fixed points. Of course, there may be 1,000 fixed points, okay, but it's a finite number. So what we're going to do now is complete our classification just for the hyperbolic maps, okay? And then we will see for non-hyperbolic maps, it's a little bit more difficult. But so for hyperbolic interval diffeomorphism, so theorem, if f and g are both hyperbolic interval diffeomorphism, are topologically conjugate, if and only if they have the same number of attracting and repelling fixed points. So notice, first of all, we'll think about this a little bit, that if the map is hyperbolic, then the attracting and repelling have to alternate, right? So if it's an interval, orientation preserving interval diffeomorphism, always orientation preserving, so we said 0 and 1 have to be fixed points, so this one can be attracting or repelling. We have two possibilities, right? If the graph goes up, then this is what? Repelling. Repelling, right? Because points are moving away. Okay? And what's the next one going to have to be? The only way it can cross the diagonal now is in this direction. Right? So once it's up, it can only cross like this. So with a derivative less than 1, it cannot, if it crosses from the left, and it must cross with, and it's hyperbolic, it must cross with derivative less than 1. If it crosses from below, it must cross with derivative greater than 1. Right? So the next one has to be attracting, right? And so on. So they must alternate. There's no other, if they're all hyperbolic, which means it's not tangent, right? If it was tangent, then you might have different configurations. But if they're hyperbolic, they must alternate the attracting and repelling. So if you fix the number of fixed points, 1, 2, 3, 4, 5, 6, 7, right? Then there will be, in this case, you have 1, 2, 3, 4 repelling, and 3 attracting, right? 1, 2, 3 attracting, okay? So if you have another one also with the same number of fixed points, then there's only the 2 options, right? There's only 2. If you fix now 7 fixed points altogether, then either you start here with an attracting one or you start here with a repelling one. Oops. Okay, and then you have 1, 2, 3. So let me do this better. 1, 2, 3, 4, 5, 6, 7. So, why are these not topologically conjugate? If they do not have, so one direction of this theorem is clear. If they do not have the same number of attracting and repelling fixed points, they cannot be topologically conjugate. Why?
Because each point would have, it would be, if they're topologically conjugate, then they would have the same alpha and omega for each point. And if they don't have the same number of attracting points, then there would be some point which there wouldn't be an equivalence or a one-to-one correspondence between the alpha and omega sets.
Okay, so let's try to use now, that's correct, let's try to use a more concise language for this, right?
Conjugation preserves fixed points.
Exactly, preserves the alpha and omega limits, that's what, preserve the attracting and repelling nature of fixed points. Yes, exactly. Okay, so topological conjugation preserves alpha and omega limit sets, so it preserves the nature, the attracting and repelling nature of fixed points. So if it does not have, and it also preserves fixed points, of course, right? So fixed points need to map to fixed points, and attracting fixed points need to map to attracting fixed points, repelling needs to map to repelling. So they can, if they have different numbers, like in these two cases, they cannot be topologically conjugate. Okay, so one direction is easy. If they have different number of fixed points overall, also obviously they cannot be topologically conjugate. Okay, so the key part of this theorem is that if they have the same number, let me draw a simplified one here because we're going to, let's just suppose we have, say, 4 fixed points like this. So, and now similar one here, where we have, so it could look very different, right? In the sense that this could be, for example, it could have like this, and like this. But they both have 1, 2, 3, 4 fixed points. 1, 2, 3, 4, right? And this one's, in this case, these are repelling, this is attracting, this is repelling, this is attracting.
Can't it be something like this? Like, we flip the order of which one is repelling and which one is, because here the first, the origin is repelling, and here is,
Yes, you're right. We could have, you're right, I'm sorry. We could have a situation where this one is, where it still has the same number, but they flipped on both sides, yes. You're right, so I didn't draw that picture, yes. So, yes, you're right. It's because I chose an odd number of fixed points, then it didn't work out. If I chose an even number of fixed points, then I could have drawn it attracting here, and it could still have had the same number. Yes. 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 In fact, I will say something. We did not discuss that case for fixed points. Okay. Let's. Okay. Yes. Let me make this comment. Well, let's look at this case first now, and. Actually, yes, that is a good point. Sorry, let me make a little parenthesis and addendum to last week's class. Right? Last week's class, we looked at the topological conjugacy between two maps, two interval diffeomorphisms that just had two fixed points, and I drew them like this. Yeah, two different fixed points like this. But what if I draw on the second one like this? F and G. Yes, so we're going to prove this theorem. So let's start. We've already proved it for the case when you have just two fixed points, okay? And when the two fixed points have the same, so we've already proved it in the case with two fixed points, and when the repelling one is near 0, and when the attracting one is near 1. Okay? So now, before we do the general case with multiple fixed point, let's just look at that variation of the argument here, where indeed you have this one is repelling, this one is attracting, but you can also have one attracting here and one repelling there, as you said. Yes. So can we do the same construction in this case? Do you remember the proof? Remember the argument? What was the argument? Using fundamental domains, yes. So are these two, according to the theorem, this also should work in this case. They should still be topologically conjugate because they have the same number of attracting and repelling fixed point, 1 and 1.
We can also consider the inverse of the function. It will have the behavior of the other case. For example, if G is like this, the G inverse would have a behavior like F.
Well, but we want to conjugate the functions, not the inverse of the function. We want to conjugate these maps. But we can go ahead exactly the same, formally exactly the same. So let's construct a fundamental domain here, X and F of X. Remember? We chose this as a fundamental domain, right? Mm-hmm. And then here, we take G, Y and G of Y. Okay? We take the fundamental domain. Yeah. And then what do? We define a map H0, a bijection, a homeomorphism between these two intervals. Like this homeomorphism does not know that we constructed these intervals just this way, it's this way. And then how did we construct the map? Suppose we take another point here, Z, right? And we want to know where it maps to, right? We're trying to construct H of Z. So how did we define?
We apply F over Z until it is a fundamental map, and then map this image.
Exactly, okay? So we wait here until we apply. We look at some tau of Z, which is the time it takes to enter the fundamental domain. Okay? And we apply this to Z, and then we apply H0, and then we apply G minus tau of Z. And where does that take us? The other side, right? So now tau, in this case, because this is the attracting fixed point, right? So all the points are moving between 0 and 1. So to go from here to here, you will move positive iterations. Yes? So then minus tau is negative iterations. So what does that mean? That we're going backwards here, right? So because all the in positive iterations you go here, so backwards here, so you will get some point here to be H of Z. Okay? And this is absolutely fine. So as you take a point that is closer and closer to 0, where is its image going to be under H?
Close to 1.
Close to 1, right? Because if you take it very close to 0, this tau is going to be very large, arbitrarily large, 1,000,000. If you take it very close, it's going to take a long time to get here. And then you get all the way to here in 1,000,000 iterations, and then you get here, and then you get 1,000,000 iterations, will take you very, very close to 1. And similarly, if you start here very close to 1, it will take you a long time in backward time, so tau will be negative. You will reach here, then you map it to H0, and then you map it in negative time, which means you get very close to 0. Okay? But you still will define a well-defined bijection, and you can show that this is a homeomorphism. It's just that in this case, this homeomorphism will be orientation preserved. The conjugacy will be orientation preserved. Right? So this conjugacy will map 0 to 1 and 1 to 0, because it must map the attracting fixed point to the attracting fixed point, the repelling fixed point to the repelling fixed point, but that's not a problem at all. It's just the conjugacy flips them around and it's a homeomorphism. Is that okay? Any questions?
Can't we note that the two functions are topologically conjugate if and only if the inverse of those two are also topologically conjugate, and then having this behavior we consider the inverse one?
I don't know, I'll have to think about that. Just like that. With the probably yes. Probably yes. I don't know. I cannot at the moment get my head around that. But this is simple. This just shows that the same argument, exactly the same, works independently of whether the fixed points are, it just gives you, it automatically gives you an orientation reversing different. So how are we going to now deal with multiple fixed points?
Just restrict to this case.
Sorry?
Restrict the interval to one of these cases and map each.
Exactly, right? Because here, actually, the dynamics, if you look at the dynamics, what is happening here is that there is some fixed points. This is P0, this is P1, this is P2, and this is P3, right? And what happens between the fixed points is very simple. Here, all the points in here, they go from, this one is repelling, so they go from P0 to P1, right? So all the points in between P0 and P1 remain in this interval, and they just move from P0 to P1. All the points in P1 to P2. So let me try to write this. I'm not sure if it's necessary, but for any two fixed points, select P0 to Pn minus 1, let's say, be the fixed points of F. Okay, then each interval Pj plus 1 is invariant, and for all x in Pj plus 1, we have either alpha x equals Pj and omega x equals Pj plus 1, or the opposite, right? So alpha x equals Pj plus 1 and omega x equals Pj, depending on the nature of the two fixed points, right? So this is here, in this particular case, you have every interval inside this, in every point inside this interval, it comes, the omega x is P1, alpha x is P0. For every x in this interval, alpha x is P2, omega x is P1. So here, the points in forward time are going like this, whereas here the points in forward time are going like this. So this is an attracting fixed point. So from both sides, it's attracting all the points on the two intervals on either side. This one is repelling. Here, this point is moving towards this attracting fixed point.
Sorry, by invariant you mean the image of this subinterval is itself, or?
Yes. Yes. Invariant. So invariant means that F. So invariant sometimes is used to mean forward invariant, sometimes forward and backward. In this case, it's forward and backward, right? So in this case, F of Pi, Pj plus 1 is actually equal to the same interval pj plus 1. And so, as you said, we can just apply the same thing. We can do the same thing, right, on each of these intervals, and the same thing here, right? So here we also have divide these intervals. This is called Q0. This one here will be Q1. This one here will be Q2. This one here will be Q3. Right? And then we can define a homeomorphism. So similarly, for Q0 to Qn minus 1, fixed points of G. Okay? And then we can define define conjugacies. In fact, we can define conjugacies Hj between Pj and Pj plus 1 to Qj and Qj plus 1, right? So we can take this interval here, P1 to P2, and then we can take this interval here, Q1 to Q2, and we can define H1, which conjugates the map 2, right? Because the map F, restricted P1, P2 is an invariant. Sorry, close up all the way to here. P1 to P2 is an invariant interval, so in some sense, as you said, you can just think of the map restricted to this interval. It is independent of everything else that happens outside, and similarly, you can think of the map G restricted to this interval, and you can do exactly the same construction. Right? And then you just define, and then H. So all these maps H, they coincide at a fixed point, because if you take H1, it maps P1 to Q1, and then you take H0, is this one here, and H0 will map P0 to Q0, and P1 to P1. So all these maps, they coincide on the boundaries, so you can just define H from 0, 1 to 0, 1, where H restricted to each of these intervals, Pj plus 1, is just equal to Hj. And this gives, it's easy to see that this gives a conjugacy. Okay, so I've assumed here in this notation that you're going to get an orientation preserving homeomorphism, but you can do exactly the same thing as in the previous case. If we had the other situation where you end up with an orientation preserving diffeomorphism, then you just need to index these fixed points in the opposite way, and you get exactly the same construction.
Sorry, can you repeat the last sentence about the other case if the order is flipping?
Right. So I don't know whether I should write it or not. So this is the way I've written it here, right? I've indexed these fixed points because I have the attracting in both cases. I have the repelling fixed point at 0, right? If your G was the other way around, so if you had the situation as we said before, where you still have 4 fixed points, but they look like this. So this one is attracting. Then you tell me, how do you do it in this case?
I go from here, from right, I consider Q0 to be 1.
Exactly. And then everything is the same, because in this case, what you want to do, what you expect, is that you will get the homeomorphism, the conjugacy to be orientation reversing, right? So you want to map the end, you need to map 0 and 1 to 0 and 1, but obviously 0 cannot map to 0 because here this is repelling, this is attracting, so you're going to map 0 to 1, right? So you're going to map this interval to this interval here, and this interval to this interval here. So you still have these 3 intervals. So the easiest thing is just to index the fixed points like this, Q1, Q2, Q3, and then everything is exactly the same. It's just these intervals, of course, I mean, yeah. It just means the interval between these 2 points without worrying about the order between these 2. Okay, good. So this gives a description of all the topological conjugacy classes of hyperbolic interval diffeomorphism, right? If you take the space, you take the set, collection of all hyperbolic interval diffeomorphisms, then how many topological conjugacy classes do we have? Sorry? You have not finitely because they may have arbitrarily large number of fixed points, but they are characterized basically by the number of fixed points, right? Or well, almost by the number of attracting and repelling fixed points.
By an order pair of integers.
Yes. Yes. Okay. So every hyperbolic interval diffeomorphism belongs to one of these countable families of topological conjugacy classes. Okay? So in some sense that is a very reasonable classification, you know, from the huge number of interval diffeomorphism. You know, you can take two interval diffeomorphism that look quite different, you know, if they might have 20 fixed points at all different lengths, but we've showed that really if all the fixed points are hyperbolic, you just count how many there are, how many attracting and repelling, and you know which topological conjugacy classes it belongs to. Okay. However, of course, we've got the ones that are not hyperbolic. So,
is this a notion of perturbation to move from one class to one class? Because one can imagine that two of these points approach each other and at some point they coincide and now we move to another
exactly, yes. That's exactly what I want to talk about now. So let me define a general notion, because when you move, we need to kind of define what we mean by moving, or what we mean by two interval diffeomorphisms being nearby. Right? What is a perturbation? What does it mean that two interval diffeomorphisms are close to each other? Okay. So there is a natural metric. So let's define. We let C1 of I equals to the space okay, for the moment let's say F I to I C1 maps, not necessarily invertible. Okay, this is a little bit more general. And C0 is equal to the space of C0, which means continuous maps. So one of these sets is contained inside the other. Which one?
C1 inside C0.
C1 is contained inside C0, obviously, because this is C1 is a special case of C0. So there are some natural metrics on these spaces. Have you studied these metrics before? C0 metric, C1 metric. Yeah?
Maximum.
Excuse me?
means maximum or?
Exactly. So the C0 metric is sometimes called the supremum, no, or the. So we can define. So C0 metric is defined where the distance between f and j is just equal to the supremum, or the if I let's put supremum, but of course if I is an interval is a compact interval, which is the setting we have, then the supremum is the same as the maximum. Right? The supremum of all x in I of the distance between f of x and g of x. So now we just do a little bit of general theory.
You want to define another metric for C1 or use the
Yes,
same metric?
yes. No, wait. So let's define the C1 metric.
Would be the sum of the supremum.
Exactly. So we can take either the sum or the maximum between the two, it doesn't really matter. We can take f of x minus g of x plus f prime of x minus g prime of x.
You took it to be the supremum each
Overall
one
x.
separately, or
You can do either one. You can take the maximum or you can take the supremum of the supremum. The supremum of the maximum.
what I meant was the sum of the supremum, not the supremum of both.
I think it's probably the same thing. I mean, it doesn't give you the same number, but it induces the same topology. What we're interested here is what it means for a sequence to converge in the C1 metric and in the C0 metric. Right? That will give essentially the same thing. So let's understand what it means. So when we have a metric, what we're not necessarily, there's many ways to define the exact metric. If you put plus here, you get slightly different numbers, but we're not so much interested in the number. What we're interested in is given an epsilon, what it means for two functions to be epsilon close. Okay, so the topology that this metric induces when you have a sequence. So what does it, what do they induce? So the C0 metric is defined for continuous functions. The C1 metric is defined for differentiable functions, but of course differentiable functions are also C0, so you can also look at the C0 distance of two differentiable functions, right? So I think something that is want to remark is, let's suppose that we have C1 functions, and it's interesting to compare the C0 distance between these two functions and the C1 distance between these two functions, okay? This can be very different. So, for example, consider the map f equals is identically 1/2. So this is just constant map 1/2. And then let's say G, the family of maps that depends on epsilon. G of x equals 1/2 plus epsilon sine x over epsilon. What does this map look like?
It oscillates around 1/2.
Exactly, let's say this around 1/2. By how much? The maximum oscillation is plus or minus epsilon, right? So here we have, let me draw big epsilon, but imagine it small. So this is 1/2. So this is 1/2. This is 1/2 plus epsilon, and this is 1/2 minus epsilon, right? So you agree that the maximum value of the sine is the sine goes between plus or minus 1. So this can go between plus or minus epsilon. So the graph of this is contained in this region of width of height 2 epsilon, and it oscillates a lot because the fact if epsilon is small, then this x over epsilon is very big. So as x goes between 0 and 1, this oscillates lots of times, right? So it kind of goes like this. I'm not sure if it finishes exactly, not necessarily, but it goes like this. Right? So as epsilon becomes small, what is happening? This is getting smaller, but the oscillation is getting bigger. More oscillations. Right? So more oscillations. Okay. So what happens is G epsilon, as epsilon goes to 0. In which metric? In the C0 metric, it converges to F, right? Because what is the distance between Fx and G of x is going to 0, because the maximum, so the supremum of all x in I of f of x minus G of x is equal to epsilon. Exactly. So as epsilon goes to 0, this supremum is going to 0, the distance is going to 0, so this is converging. So G of epsilon converges to f in C0. What about in C1? In C1 not, right? Because the derivatives, it always has some places where it has very large derivatives. In fact, as epsilon goes to 0, it will have larger and larger derivatives, in fact, whereas this one has derivative 0.
Would it have larger derivatives?
Well, because it has to oscillate more in shorter and shorter space. So the derivative, I think, at these points here is going to infinity. Right?
No, but also the height.
Oh, also epsilon. Okay, you're right. I'm not 100% sure it has.
No, we can calculate this explicitly.
Yes, you can calculate it explicitly. You can do it as an exercise. But certainly it does not go to 0, the derivative, for sure, because it keeps oscillating. So yes, you can do explicit calculation and you can check that, yes. Okay, so but G epsilon does not tend to F in C1 metric. So this means that two functions may be very close in the C0 metric, but very far in the C1 metric. So when you talk about a perturbation, it makes a big difference when you say, okay, can you make a small perturbation of your map if you say you want to perturb in the C0 metric or in the C1 metric. Okay? So let me define now the notion of structural stability. So definition.
Can we take 2 minutes break?
Yes, okay. Let's take a couple of minutes break. Thank you. It's a good idea. 2 minutes. Okay, so yes, so the way we use this metric is to define a very, very, very interesting concept. So this we can define for any dynamical system. So this is not just for I've defined these metrics just, so I'm not sure whether to define, let me define it just in this case. So an interval map F an interval map F in C1. So a C1 interval map F is structurally stable. If there exists epsilon greater than 0, such that for every C1 interval map G, such that with the C1 distance between F and G is less than epsilon, then F and G are topologically conjugate. So what we're saying is that if this is somehow the space of all C1 interval maps, right? You take one F here, you take the C1 metric, and you say there must exist some neighborhood. So this is what we mean by small perturbation. So we fix the topology of the of what we mean by small perturbation in this C1 metric. So every map that is C1 close to F is topologically conjugate to F. So you cannot leave, it's not on the boundary of a topological conjugacy class.
But what is an example of such a function on the boundary?
Okay, we will look at these examples now. So the reason I was hesitating when I was writing this is because I didn't know, in the notes I write this in a little bit more generality. So the standard, in some sense, so there are various options, right? Why did I choose C1 here instead of C0? Why did I choose topological conjugate and not C1 conjugate, for example? Okay, so I could define different notions of structural stability by allowing myself to take, suppose I could define a much stronger version of structural stability if I said, if I put 0 here, right? Can you see that this would be a much stronger notion? Because I'm saying that I want epsilon, and every map that is C0 close epsilon should be topologically conjugate. Why is that a much stronger notion of stability?
Because you have more function in this neighborhood.
Exactly. You have many more functions which are C0 close, as we said before. Okay? So I could say that I want the structural stability for C0. Also, I could say that I want these to be C1 conjugate. Okay, this would also be a much stronger notion. I'm saying that there should be a whole neighborhood here where every map is not just topological conjugate, but is C1 conjugate. Okay? And similarly, you can also have the metric C2, C3, CR, C infinity metric. So there's a whole range. Just like the conjugacy, you can acquire different regularities. Okay? So I will mention the reason why I like this is because this is the one that makes more sense. Again, it's a similar observation to what I said before. And generally, if you assume, if you put C0 here, then almost no map will be structurally stable, because it's very easy to approximate a map in C0 by another map that has completely different behavior, which I'll see some example here. And similarly, if you put differentiably conjugate here, also almost no map will be structurally stable, because you can take C1, but if you change the derivative at the fixed points, then you lose the C1 conjugacy. Okay, so this is in some sense, the structural stability that seems to make more sense is where you have the C1 metric here and the topological conjugate here seems to be the one. But I just want to emphasize that there is, this is not God-given, right? We choose this particular definition because it works and it helps us to understand things better, okay? In certain situations, we would like to know what differentiable conjugacy or C0 or various variations of that. Okay, this is just an observation about this. So, what is our theorem? theorem is that f is a hyperbolic, is a C1 hyperbolic interval diffeomorphism is it going to be structurally stable or not?
Yes.
Yes. Okay. Then f is structurally stable. So I will sketch the proof of this, and then I would like you to make sure that you complete the proof, right? But first, let's just quickly look at what happens if it's not hyperbolic. Can it be not structurally stable? So if f is not hyperbolic,
Because of this tangent, can you just move it a little bit?
exactly, right, exactly. So we can have a map, for example, that has a fixed point as a tangency like this. So here the derivative is 1, and you can see that in the C1 metric, so you can keep the derivative almost the same here, but you can define something that does not have any fixed points here. Or you can define something that has 2 fixed points instead of 1 here. Right? And you can do it by keeping the derivatives very, very close as you want. Okay, so you can perturb the map to a fixed point can disappear, or 2 points can be created. It's very interesting what happens here. And so, of course, this map cannot be topologically conjugate either to this one or to that one because they have different number of fixed points. This is sometimes called a bifurcation. If you're on the boundary, so this map is in some sense in the boundary, right? By that theorem, these 2 maps that you get are structurally stable, because now we will look at the sketch of the argument, but if the fixed points are hyperbolic, then you can, intuitively it's obvious, you just cannot perturb them, you cannot change them. If you take something, a map that is C1 very close, then you cannot change them, right? So this is called a bifurcation. So there's a whole area called bifurcation theory, a whole area of dynamical systems, which we're not going to talk about, but it's very interesting. This could be, for example, if some of you is interested, it might be a nice topic for a diploma project in interval maps to actually study the bifurcation. We are concentrating on the structurally stable systems, but you can also just as much be interested in the systems that are not structurally stable, which by definition are called systems that have a bifurcation because arbitrarily small changes change the topological conjugacy class. And there's a study of, you can study these bifurcations in a very systematic way, so it's very interesting. Okay, so let's see roughly why the system is structurally stable. I'm just going to sketch the argument, right? So, just as an example, let's just take this example here. How would you prove? What do we need to show? So we want like this, so this is a map F, right? And then we take some G such that the C1 metric is less than epsilon for some very small epsilon. And we've already established some criteria that determines that 2 maps are topologically conjugate. What are these criteria?
The number.
Exactly. So if both f and g are hyperbolic, and they have the same number of attracting and repelling fixed point, then they're topologically conjugate. Okay? So this is a key ingredient in the proof. So that's what we're going to show. So we're going to show that if we take G sufficiently close, you cannot change the number of fixed points. And they remain hyperbolic and they have the same number of attracting and repelling fixed points. Okay? So here there's 3 fixed points. But in general, we know there's a finite number of fixed points. Right? So we can, first of all, let's kind of separate the regions where there are fixed points and where there's no fixed points. So so these are fixed points, as we said before, P0, P1, and P2, but you can do it for the finite number, right? So the first thing we do is let's call this neighborhood a neighborhood of P0, and then a neighborhood of P1, U1, and then a neighborhood of P2, U2. Okay? Because this is really we're going to do 2 different things inside these neighborhoods and outside these neighborhoods. So what can you say about what happens outside these neighborhoods?
There will be no fixed points.
There are no fixed points, and how do we guarantee that G has no fixed points?
By assuming some.
Because fx minus gx is time epsilon. Always.
By limiting the values of the.
Yeah, right.
Limiting the values of the function to be away from y equals x. So we the distance should be strictly greater than or less than or equal to the distance from y.
Does that make sense to everyone else? This is the same as what you were saying, I think.
Maybe.
Yes, so we need to work on the language here, yeah? We need to work on the language. Because you can figure it out, but you need to be able to say what you mean. Yeah? So, which is not easy. I mean, a big part of mathematics is knowing how to say what you want to say. So, the first observation is that if you take the map outside these neighborhoods, the distance, the C0 distance, so you look at this part here of the graph. I should really bring some colors here for next time. So, and this part here of the graph is bounded away from the diagonal. I think this is what you were saying, right? So there's if you look at the distance here from the diagonal and the distance here from the diagonal, right? So proof, let's sketch the proof. You need to make sure you fill in all the details, right? Let Uj be neighborhoods of the fixed points.
Shouldn't we start with
Pj.
neighborhoods? Shouldn't we start with the neighborhoods?
It doesn't matter, they're 2 independent arguments in some sense.
But the.
So, sufficiently small neighbors, yes. So these let Uj be sufficiently small for the argument that we're going to need.
Yes.
Right? Yes. Sufficiently small. For example, you need to make sure that each neighborhood contains only 1 fixed point. Okay? This is not obvious. Now here it's obvious, but if there's 1,000 fixed points, you will need to take these neighbors very small. Okay? So you can choose. So maybe I should say it is possible. So there exists Uj neighborhoods of fixed points Pj, okay, satisfying certain properties. Okay, so that the outside these neighborhoods, so that f of x minus x is greater than or equal some delta greater than 0 for all x which is not in the union of these neighborhoods. So there exists some delta such that here this is delta, right? So everywhere outside these neighborhoods you are delta away from the diagonal. Okay? This means what? That any perturbation, as long as G is C0 metric less than delta, then it will be okay. You cannot create any new fixed points in this region. Okay? So as long as the zero distance is strictly less than delta, okay, then G has no fixed points outside in the union of these UJs. Okay, so we take G because what does the C0?
I think outside.
Sorry, yes, that's what it is. Outside the union of UJs. So that's fine. So we're guaranteed that we cannot create new points outside these UJ, new fixed points. Now we need to worry about whether we can create fixed points inside the UJs. Okay? So this is a kind of local argument. So again, let's kind of zoom in here and see what's going on, right? So we have the derivative, we have some fixed point here, P, we have some neighborhood here, and how do we guarantee that we cannot create any new fixed points?
By the continuity.
By the continuity of what? So how do we,
Derivative.
of the derivative?
Yes, because if there were okay.
With this metric, you can keep the derivative as small as you want, or as near as the other.
As close to this as you want, exactly. So this map, we need, so let's, sorry, I really need some colors here. So our new map G will be inside an epsilon neighborhood, right? This is plus epsilon minus epsilon. Now, if we perturb in the C0 metric, could we create some new fixed points?
Of course. But
Yes.
Sine C.
Exactly. So in the C0 metric, we could take, when we come very close to here, you see, this neighborhood includes the diagonal here. So all we need is, for example, to do something like this.
Yes.
This map will be C0 close to F, but it contains some additional fixed points.
If there are two fixed points, then by the mean value theorem, there will be a point between them which has derivative 1.
Excellent.
And we can bound the derivative inside this neighborhood that we...
Excellent. Perfect. Okay? That is exactly the proof. So if so we need to use the fact that so inside UJ, so we can choose UJs, okay, by similar argument to what we had before, we can choose UJs because the derivative here is strictly different from 1, right? And either less than 1 or bigger than 1, in this case it's less than 1, we can choose the neighborhood small enough so that the derivative everywhere is strictly bounded away from 1. Okay, this is the first choice. So we can choose so that f prime in uj strictly bounded away from 1. Okay? And we can do that maintaining this delta. So in some sense you're right. Maybe we should have chosen that first, because actually this holds whatever neighborhoods you choose. So here we need to make sure the UJs are sufficiently small, okay? But once we've chosen the UJs, then we always have, these are kind of two properties that we're going to have. Once we've chosen the UJs, this comes automatically that they exist some delta. But choose UJ so that f prime in UJ is strictly bounded away from 1. Okay, then by contradiction, if G has two fixed points in some uj, then there exists a point Q in uj such that G prime of Q is equal to 1. But how do we conclude? How do we conclude the last bit? Why is this a contradiction?
Because we have a true.
Wait. So, if G has two fixed points, right? So suppose now that we had two fixed points like we did before. Or even just, two fixed points, or more than one fixed point here. So wait, maybe I should draw a bigger version of this. Right, so. Okay, let's choose epsilon big, just to simplify, okay? So we are inside this epsilon, and suppose that we have now more fixed points instead of one. Then by the mean value theorem, if it has at least two fixed points, then by the mean value theorem there must be some point here where the derivative is 1, the slope is 1. And why does that give a contradiction? Wait, let's see if we... Sorry, you said?
Yeah, we see one hyperbolic, its derivative is ICTP.
No, the derivative at the fixed point cannot be equal to 1, but somewhere else it can be equal to 1. In fact, remember here, that's a good point here. So remember that you always have points where the derivative is equal to 1 between, when you have several fixed points in between the two, it's just not, hyperbolic means that you cannot have derivative 1 at the fixed point, but you can have derivative 1, you must have derivative 1 between two fixed points, right? Because this is the mean value theorem. If you take f of p equals p, equals p, so there must be some point in between where the distance between f of p1, f of p0, and f of p1 is equal to the derivative times p0 minus p1, and so there must be a point where the derivative is 1. That's the mean value theorem. But why does this give a contradiction? So we choose uj so that inside we have the derivative on uj strictly bounded away from 1, okay? Which means that if you take your epsilon sufficiently small, then you're saying that you want, if you take epsilon sufficiently small, so that you are asking, requiring that the derivative of g also is bounded away from 1, because suppose f is bounded away from 1 with some lambda less than 1, then you take epsilon smaller than the distance 1 minus lambda, right? And then the derivative g must also be bounded away from 1. Okay? But if there's two fixed points, as you said, then that means there must be a point where the derivative is 1, which contradicts that fact if you've taken epsilon sufficiently small. Make sure you revise, you understand this side. Impossible.
Also, the solutions appear if V and hyperbolic have a finite number of hyperbolic points, right? Because eventually we will want to take this epsilon to be the minimum of all epsilons for every point.
Yes.
What do we prove?
Yes. Yes, we have a finite number, yes. Yes. Okay, so I just sketched it here, yeah? So you should make sure this is also a good candidate for the exam question. Okay, the proof is really not difficult, but you need to make sure you understand it. And it shows that it kind of is the main motivation for topological conjugates. So structure, I know we're running late, just give me one more minute because I'd like to make a general comment about this. So the notion of structural stability is a very classical notion. It comes from the 1920s and 1930s. And the philosophy of this is very natural, is that if you're using dynamical systems or differential equations to model some real-life phenomena, right, then you say, well, okay, you know, there's always some small mistakes I'm making, both in the creation of the model, and then again there's this other issue of the sensitive dependence on initial conditions, but even forgetting that is in the creation of the model. You know, maybe my model is not exactly accurate, Okay, so okay, you say, well, it might not be exactly accurate, but if this model is structurally stable, then if I made a small mistake, it does not make necessarily a big difference. At least it means it's still topologically the same. Okay, of course, there's many issues with questions exactly what this topological structure, if it's enough information or whatever. But this is the basic philosophy, is that structurally stable is a very important property. Understanding which dynamical systems are structurally stable really means that they are robust in some sense. Okay, if you shape them that way. Okay, thank you very much.